This is Lab 1. In particular, this is Video 1. There'll be 3 videos in this lab. The first one deals with an MM1 queuing system and the solution methodology that we'll use for the entire queuing analysis section. So the system we're going to look at has a single server, a single queue, arriving customers, and we're going to assume this is, as I said, MM1. We're going to assume that we have an arrival rate lambda of 48 customers per hour and a service rate mu of 60 per hour. And what we're interested in is at steady state, what is the utilization of the server, how many entities are in the system on average, and what is the time in the system. So this is utilization. This is the number of entities. This is the time that an average entity spends in the system. Since our system is MM1, go back up here, where our M's in this case stand for Markovian, we know that our inter-arrival times, which we're going to call IAT, will be exponentially distributed with a mean of 1 over 48, that should be an 8 here, 1 over 48 per hour. And I'm going to work in minutes here, so this is equivalent to exponentially distributed with a mean of 1.25 minutes. Similarly, our service times are also exponentially distributed with a mean of 1 over 60 per hour. Again, converting that to minutes, exponential with a mean of 1 minute. And so we can work in either time units that we want. We can either work in hours, where we have the 1 over 48 and 1 over 60, or we can work in minutes. We just have to make sure that we pick one or the other and that we're consistent. And so let's look at what this means. And so I've pulled, using the MATLAB dist tool in MATLAB, the probability density function and the cumulative distribution function for the exponential distribution. In this case, I'm using the inner arrival time distribution, so a mean of 1.25 minutes. And we can see the density function over on the left and the CDF over on the right. And as we know, this exponential distribution is highly variable. And so if we think about an inner arrival time, we have a whole lot of inner arrival times that are actually less than 1 minute, even though our mean is 1.25 minutes. And so if we look at in the dist tool, this is telling us that at 1 minute, the probability, the cumulative probability, is 0.55. So over half of the total probability is less than 1 minute. So what we're going to see is a lot of short inter arrival time. So a lot of entities arriving with short time in between arrivals. However, we also know that the exponential has infinite tails, and so we also will see some rather large inter arrival times. So that's what I mean when I say it's highly variable. For this lab and this class, we're not particularly interested in the theoretical development. I assume you've already seen that. So we're going to make an assumption that we have available for us when we have an MM1 or an MMC queuing system. We have the following table of expressions that give us the performance metrics that we're interested in. And so again, you can look at any stochastic OR book or queuing analysis book for the development, but we're interested here in the application. And so if we think back to what we're after these 3 values at steady state: the utilization of our server, proportion of time that it's busy, the average number of entities in the system, and the time that the average entity spends in the system. For an MM1 queuing system, these are all easy to compute. We know, not go back that far, that the utilization is equal to lambda over C mu. And so our server utilization, again, it doesn't matter whether we use hourly rates or minutes, as long as we're consistent. So I'm just going to use hourly rates. So it's 48 divided by 1 over 60. And so we would expect our server to be busy 80% of the time. From our table, we can also get the average number in the system and the average time in system using the expressions given. And so L for our case is rho over 1 minus rho, which is equal to 0.8 over 1 minus 0.8, which ends up being exactly 4. And W is equal to 1 over mu times 1 minus rho. And so in our case, this is 1 over 60 times 1 minus 0.8. And so this ends up being 0.0833 hours, because I chose to use hours as my time unit here, which is equal to exactly 5 minutes. So what this analysis tells us is that at steady state, if we have an MM1 queuing system with an arrival rate of 48 entities per hour, service rate of 60 entities per hour, that we would expect the utilization of the server to be 0.8, for there to be 4.0 entities in the system, and for the average entity to spend exactly 5 minutes in the system.